Okay, HEC-RAS. I have already installed the HEC-RAS software in my computer, so just simply click on the icon to start the software. And the first step is to create a new project. We can put it anywhere. I have already created my folder. That is Morge 3. It has an S actually, Morge. And the name of the river is Boao, which is located at Morge avec S, with S. The new project is now already created. The next step is to make sure that the unit system is in US customary unit metric system. Okay, a metric system, and set it as a default. That's all. Then the third step would be to add some geometrical data of the river. Then the next is hydrological data, discharge, and so on. Click here. First we have to create a file for geometrical data as well, and just call it geometry of Poiron, and then click. Now the file is already created. Now click on this river ridge. Just hold on the left part of the mouse and pull it down, and just double click at the end. Then a pop-up window will come up. Then just simply put the name of the river, Baron, and just simply the name of the ridge. Yeah. Now we have the direction of flow, the name of the ridge, and also the name of the river as well. The next step is creating the cross section, or pressing the cross section data. Just simply add just simply give a name, cross section 1, and let us see the site first. Just this is the map or the plan of the site. At the left side of the bank is covered with forests, as indicated in the plan, and it's just trees. And there is also an asphalted road. There is also a plan to construct a new canal, which doesn't exist at the moment. This is just simply a plan. Yeah, that's a plan. This one is the river. The cross section is given, so there are 14 cross sections, and as HEC-RAS processes the data from the downstream to the upstream side, then the first cross section will be the one which is located at the downstream side. the other side of the bank is also covered with forests, but um, a little far from the bank there is an agricultural field. That's all. So the data is already, cross-sectional data is already given here. We just simply copy the data and put it in the software. Just select and Control V, then apply data. That's all. The cross-section, already cross-section number 1 is created, and the next cross-section number 2, just this description, cross-section 2, and we just simply go to the Excel file and copy and paste it. Just simply Control V, apply that one, and option again you just simply number 3. It's just simply unnecessary to show all the steps because it is similar, so I think it is better to jump into the next step. It's just simply a repetition. And 13, the last one is 14. The cross section which is found at the far end of the upstream. So we have already completed. Then it's good to save it now, and all the cross sections are in place, and we need to put them the distance between the cross sections, and also the left bank and right bank, and also the manning and value. These are the data we need to put. Yeah, of course the distance between the two, we assume that it is equivalent. I mean the right bank and left bank distance and the center as equivalent, but there might be a little variation. It's okay. It's almost equal. The distance from the lake to the first cross section is given, that is 50 meter. We can see the distance. Yes, that's distance between the profiles. So the first is 15, and the distance, copy it, and to add new cross section, table and right angles. Just simply paste it. Control V, Control V. Let's finish. All the reads are now in place. You can see all number 8. Now the morning end values, we have to also bring them here. Just simply to check how well the end values. Just let us see some notes. Just simply notes. K strike is equal to 1 over n. It means so these are given, you see. Just simply we can select the n value based on the pictures, comparing with the real state of of the river, our river. Yeah, so just simply here for this type of river, which is lined canal and so on, K is given that is 45, and also for the other one, for picture B, also 42 given. So just by comparing our river real situation with the picture, then we can choose the K value and calculate n. You see, our situation is just similar with the one which is black and white picture. We can see this is a real video. This is the lake. This is the lake. That is the level of the lake where the river enters into. It's the mouth of the river, I think. There is some kind of deck-like structure which covers. That's because it's just simply to protect the lake from some kind of fertilizer, chemicals and so on. You see, they can't just simply enter directly into the lake, but you see that dike help the chemicals and the pollutions, they can't pass to the lake and pollute the lake. So that is the importance of just constructing a deck at the mouth of the river. You can see the bank is just very nice, covered with forest at the left and right side, and the bank is in good condition, in a perfect condition, I can say. It's good. The density of the tree is not much. It's not very dense, but the trees is it's almost similar. You can see. It's not actually exact, but almost similar with this one. So just for our calculation, simply let us consider this one. Take 31, K strike 31, and let's go to the table. In the table, you just go to the perfect, means perfect type of bank, and bone means it's okay. The state of the bank, it means ita de parwa, means so acebo means less than, is sufficiently good. Movies means movie means it's bad. So if we can consider 30 for K strike, for example, here the n value would be 0.033. We just simply go to the 0.33, percentage 0.33. And also there are graphics for just to see the K value in the bank, and we can see that our situation is like, I think K is pathetic, or maybe around K strike around 10, I think. I'm not sure, but it's just subjective. It's just judgment. You see, you just simply see the bank and just take the number. I mean, so let us see for 10, for example. Okay, let's see 15. So for 10 that's 0.1, and it means zone avec beaucoup de mauvaises herbes, means a zone with a lot of herbs, bad herbs. The other one is just zone ou courant lentement avec herbe ou fossé très profond, means a profound, deeper ditch, down which has a deeper ditch, and water flows slowly over the herbs. It means. So maybe just simply let us consider for the calculation. You just let us say it doesn't matter. It's just simply just let us consider 0.03 just for the calculation purpose. Yeah, both sides the same. So we assume the n value for the ridge is the same, so we have to put for each cross section similar values, and to put that we have to go to the table and just simply put or insert the values. Just simply copy and paste to all cross section. That means our assumption is all the bank has similar roughness coefficient, and just the roughness coefficient of the river, just the center of the river, and just inside the river is 0.03, because there are some boulders and so on. And so it's just a matter of looking into the situation. So now, which one is the left bank? I mean the border of the left bank. Which one is the border of the right bank? I mean we have to tell to the software that this one is the border of the bank. This one is the border of bank. If something, if there is overtopping of that bank, that is the upper limit of the bank where the water should be contained in. You see, if there is something which is above the border, then that is an indication that there would be overflow. There is an overflow, it means. So we have to inform to the software that um, this is left bank and this is the right bank. So later it will help to analyze the situation of the banks in relation to the inundation or something like that. We just put for each and every cross section just the border or the bank, the limit of the bank where the water should be contained in. So we can see from the cross section, and we can just simply put that red dot at the right and left bank. You see the number which is above the banks indicate the n value. That's for the left and the right, that's 0.06, and the middle part is 0.033. It means actually we have to make those things, I mean, in a perfect situation, so that to minimize errors, we need to make sure that the n value aligned in a perfect place, in a place where we consider that the n value is this for this one and this for this one. So we have to make it right, you see. But because this is just simply an exercise, no, we don't have any problem. Now we have already placed the data. We have to save it now. Everything is done now. So the geometry is saved. We have geometrical data. This is just leave it as it is given. It's okay. So this is all about adding geometrical data to our analysis. So you see we have already a geometrical data, geometry of power. To put the hydrological data, let me stop and see, because I have already done the geometry of power corrected well. So let us put the hydrological data. To put the hydrological data, just simply click this one and just simply, because we have 9 profiles, just we have to put all the 9 profiles. there are known values. You see known values here. For example, upstream and downstream conditions are. The downstream condition is known. The elevation is known. It means the the sea level. The sea level is just known at the Geneva. The dam has already regulated to a level of 372 and 90. That is the elevation of the lake. Just you just close the gate of the dam at this elevation. Always it is the same. So at the down reach of the lake, you see the water level is the same. So we can consider that um, the the downstream elevation level is always 372.30. Just taken from the level of the dam. You see, so we can put that one in the table 300. The level, the first level, at zero, it means. The upstream elevation is just consider as it's a depth, a critical depth. It's just we can see from the upstream side where the 14th. This is just the where the number 14 cross section is located. You can see that there is a critical flow. We can say let us assume as a critical flow. So, yeah. A critical flow has the fraud number 1. There is also supercritical and yeah, the supercritical one has the one which has hydraulic jump and so on. There is also subcritical flow. Mostly rivers do flow in a subcritical situation. Let us change this one, just profile 1, but instead of profile 1 2, let us name Q300. It means Q347 is a given in here in Switzerland. They just know it that Q347 is a flow, a discharge level, and a dry state. You see, the dry flow. So they call it Q347, and it's known. Then the 2.33 years. These data are given already. It's just simply an exercise. So the for 5 year and 10 year and so on up to 300 year. That is the recurrence period or recurrence interval discharge value for 5 years, 10 years, 100 years and so on. You can change that now. 20 years. Yeah, it's already, they have already here a record, so data is available. So you just simply put all those data, insert all those data as that's so you see, from the given data, the the flow, which is the dry flow, see, that is 0.57. They call it, it has a name, see, Q, a designation, Q347, they call it. That means when they just say Q347, it means it's the driest flow. And for other river, maybe Q347 may change, but for Boiron River, it is 0.57. And the other periods given is just given 17 and so on, T15 17.9. Just given values. No, just now save the hydrological data. That's Baron hydrology. Just this is naming. Okay. Now everything is done. You see, geometrical data is in, hydrological data is. That is a spelling error. Hydrology. It's okay. Well, so to create a plan first, a name simulation plan. Just simply just create a new plan and simulation number 1, something like that. And the short name sim1 as well. It's just simply then compute. If there is any error in, say, geometrical data on hydrology, it won't it show us an error message. So it's already, the simulation is already now in. Now to see the results, we just simply see, you see, this is for example Q driest. You see, the driest means it doesn't, for 300 the river at cross section 14, you can see the level of the flood is okay. Okay, the dotted green line is just the energy grid line of flow. Number 8 has some, just some, see, overtopping. It's just like flooding, you see. HEC-RAS always consider that, just, you see. It means actually it might not be a flooding, but you see the water level, when the water reach up to that level, might be, it's just the water just maybe seep through the bunkers, I think. These are the profile of the wall, the energy grid line, and also the profile of the river. So you can see clearly from the results that some of the areas where the water may overtop, you see. It seems a very small area, but when you calculate the length, it might be very long, And if there are some structures like buildings and so on around just by the side of the embankment, maybe the water may flow out over top those areas, and it might it may damage the structures, the buildings and so on. So it needs some maintenance here, you see, like gabions and so on, just simply to cover. We can calculate the distance, you see. You can see from 7 up to from the 7th station up to the 10th station, it is almost 140 or something, 142 to 188 means stations distance. Uh, 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 okay, 46 meter, I think that's 46 meter. And also here also we can see that there is some problem. Might be, you see, we have to double check how we run the model, the geometrical for example the right and left bank and so on, to verify that it is really an inundation or something like that. So as 13 we see there is no problem. You can see from the picture here, but you see from the longitudinal profiles we have seen something different. So we have to double check the error, where we made the error and so on. Get, you see, just try to make it right, you see. So actually the software only give us some estimation. It doesn't, we have to be in the place and check whether it's true. We have to compare with the natural situation of the river. So we just let us check the cross section and correct the problem. So maybe add the, okay, you see the, just simply we can add some by the embankment is high, but you see the HEC-RAS assumes only the bank which we have given. So that's how it operates, you see. If we give it an incorrect bank, then the result also becomes incorrect. So just simply create a second simulation, correct the geometry, run again. Simulation number 2, just simply borrow. It doesn't, the name doesn't have importance, just simply it is a designation. Same to just simply to just designate, then copy, compute, save the plan. It's finished. Now we have born to, we can see now it's alright. The longitudinal also is okay for, yeah, there is no problem. Yeah, it was a mistake. Maybe here also we need to check, but I think this might be needs some maintenance. You see, because of the scale it seems like a V shape, but when we stretch it, this is just not like, in reality it might not be like that. Just 100 Just 40 meter. It seems a triangular shape or something like that, but just consider it as some kind of, say, low level where the flood can escape to the left and right bank, and might just cause some damage to the surrounding areas, especially if there are structures, buildings. So that might be. You see, HEC-RAS used to to calculate, you see, the insurance premium as well. If there are buildings which are located in vulnerable areas, the premium will increase. See, the insurance they pay. That's also very important. HEC-RAS is very important for many things. We just can copy the data, just simply to copy and see the velocity, the area of the flow, and so on. Just simply just to see. See, is this is a 400 years, 100 recurrence interval in the front number, top is everything calculated. You see, HEC-RAS is intelligent. Now, just simply we can save the project and close, generate report. That's all. Yes.